Okay, friends, very good evening. Again, we are going to discuss about distributed systems. So, there are two important regions of operating frequency distinguished by weather. One may treat circuit elements as lumped or distributed. The fuzzy boundary between these two regions concerns the ratio of the physical dimensions of the circuit relative to the shortest wavelength of interest. At high enough frequencies, the size of the circuit elements becomes comparable to the wavelengths, and one cannot employ the impurity intuition derived from lumped circuit theory. Next, wires must then be treated as the transmission lines that they truly are. Kirchhoff's law no longer hold generally, and identification of R, L, and C ceases to be obvious or even possible. Okay, Maxwell's and Kirchhoff's law. Maxwell and Kirchhoff's laws are approximations that hold only in the lumped regions. They are derived from Maxwell's equations if we assume quadratic behavior, thereby eliminating the coupling terms that give rise to the wave equation. To understand what all that means, let's review Maxwell's equations for free space in differential form. That is, del dot mu naught h is equal to 0, del dot epsilon naught into E is equal to rho, del cross h is equal to j plus epsilon naught into rho E by rho t, and rho cross E is equal to minus mu naught into rho h by rho t. The first equation says that there is no net magnetic charge. So there are no magnetic monopoles. The second equation acknowledges that there is net electric charge and says that electric charge is the source of divergence of the electric field. The third equation states that the both ordinary current and the time rate of change of the electric field produce the same effect on the magnetic field. The term that involves the derivative of the electric field is the famous displacement current term that Maxwell pulled out of thin air to produce the wave equation. Finally, the fourth equation says that a changing magnetic field causes curl in the electric field. The line integral of the electric field around any closed path is zero. This is merely the field theoretical expression of Kirchhoff's voltage law. To derive KCL, we proceed in the same manner but not set epsilon naught equal to 0. Then the curl of H depends only on the current density J, allowing us to write del dot J is equal to del dot into del cross H is equal to 0. That is, here the divergence of J is identically 0. No divergence means no net current buildup at a node. Of course, neither mu naught and nor epsilon naught is actually zero. To show that foregoing is not hopelessly irrelevant. As a consequence, recall that the speed of light can be expressed as c is equal to 1 by square root of mu naught into epsilon naught. Setting mu naught or epsilon naught to 0 is therefore equivalent to setting the speed of light to infinity. Setting mu naught or epsilon naught to 0 is therefore equivalent to setting the speed of light to infinity. Next, hence KCL and KVL are the results of assuming infinitely fast propagation, and also we can expect them to hold reasonably well as long as the physical dimensions of the circuit elements are small compared with a wavelength, so that the finiteness of the speed of light is not noticeable, so that the L is very lesser than the lambda. where L is the length of a circuit element and lambda is the shortest wavelength of interest. And now we are going to know about the transmission line. So what are these transmission lines? A transmission line basically consists of two or more parallel conductors used to connect a source to a load. The source may be a hydroelectric generator, a transmitter, or an oscillator. The load may be a factory, an antenna, or an oscilloscope. Okay, the load may be a factory, antenna, or an oscilloscope. Next, the transmission lines are looks like simply for microstrip dimensions are like that, and microstrip dimensions are like that, and microwave waveguides are looks like that, both for circular waveguide and rectangular waveguide. And fiber optical cable also seems to be like this. So inside the fiber, inside the conductor, there should be the coating of glass. Again the glass is coated with glass, and lastly buffer coating will be present on that optical fiber cable setting. So here the transmission medium is fixed in between the source impedance and the load impedance, and these transmission mediums are mainly divided into two types. One is lossless transmission lines and number two lossy transmission lines. So here two parallel conductors are there. The two parallel conductors shape is like this. Inside the conductor what should be present means resistance, inductance in parallel with the capacitance. Okay, so this is the lumped RLC model of infinitesimal transmission line segment. Now we are considering the small portion of the transmission line, and we are finding the inductance, capacitance and resistance value with respect to unit length. Okay, with respect to unit length. And next one, lumped RLC model of infinitesimal transmission line segment is looks like that. Okay, to derive the relevant parameters of a lossy line, consider an infinitesimally short piece of line of length dz. Here the length elements L, R, C and G are all quantities per unit length. Okay, the inductance accounts for the energy stored in the magnetic field around the line. The series resistance accounts for the inevitably energy loss that all ordinary currents exhibit. Okay, the shunt capacitance models the energy stored in the electric field surrounding the line. The shunt capacitance accounts for the loss due to mechanisms such as ordinary ohmic leakage as well as loss in the line's dielectric material. So, characteristic impedance of a lossy transmission line. How can we find out the, how can we derive the characteristic impedance? Okay, from this circuit we can be analyzed that both input impedance and the load impedance both should be equal to the characteristic impedance. This is according to the maximum power transfer theorem. The main intention of this maximum power transfer theorem is ZL is equal to Z0 is equal to input impedance. And now here that when the two resistances are connected in parallel, so what is the condition when they are connected in parallel means R1 into R2 by R1 plus R2. Now we are implementing the same equation, same formula for this circuit. Okay, and now I am deriving the input impedance, that is Zin is equal to Zin is equal to input impedance means what will be present here? Z input impedance means without applying the uh, dz. Okay, z plus 1 by y is parallel to z in. Okay, next for output admittance we are deriving the same formula, that z naught is equal to zd. We are just adding the dz element. Okay, z dz plus z naught by 1 plus y dz into z naught. Here it is the condition for the parallel. Okay, y 1 by y is parallel to z in, and y 1 by y is parallel to series condition. Okay, next We will consider here this equation we will can be written in the form of 1 by 1 plus x. So what is the binomial first order binomial expansion of this equation is it's to 1 by 1 plus x, it can be written as 1 minus x. Okay, it is the solution for the first order binomial expansion. Okay, so z naught is equal to, simply we are writing the equation as z dz plus z naught into 1 minus y dz into z naught, and we are again rewriting this equation as z naught is equal to z naught plus, we are getting or we are taking the dz common for both terms. Okay, we are from the both terms we are taking the dz components constant. Okay, dz